Alright folks, so in this video we're going to review Chapter 7.1, in which we discussed this new concept of a sampling distribution, and this was the sampling distribution of the sample mean, and we will also touch on the central limit theorem. So recall that a sampling distribution is a probability distribution about a statistic. That's why it's regarded in regards to the sample mean. And so we want to know how this statistic, the sample mean, is distributed, so that way we can make inferences, statistical inferences, in the near future, and that will be in Chapter 8. So when we want to discuss properties of a distribution, we generally like to mention what is the shape. We like bell-shaped or normal curves. What is the center of that distribution, and the spread. So we will start there. So let's first talk about the shape. As mentioned, we like to work with normal distributions. So when can we satisfy that? So we said that the sampling distribution of the sample mean will be approximately normal if either of the following is true. So if the original population, is normal, that would usually be some information given in the context of a problem. Or, regardless of the shape of the population, like what if you can't satisfy that? Then that's where the central limit theorem comes into play. Or, according to the central limit theorem, I'm going to reference that a bit, so I'm going to abbreviate CLT, which states, the central limit theorem states that regardless of the distribution of the population, regardless of the shape of the population, the sampling distribution will be normal. The sampling I'm going to say the sampling distribution of x bar being the sample mean, the sampling distribution of x bar will be approximately normal for sufficiently large sample sizes, and as sort of a easy way to remember that, we'll just say sample size at least 30. In general, we're going to be working with normal distributions, and so one of those two criteria will be met. It's possible both might be met, but at least one for sure. Now, once we've got the shape being normally distributed, now we can talk about where is its center. What is the center? If we're working with a normal distribution, then we want to discuss the mean as the center. And you may recall this notation where we say the mean of all possible sample means is the true population mean. So that's quite a nice property there. Once we've got the center established, now we can talk about how spread out all the theoretical sample means are. So now let's talk about the spread, or dispersion. So this is the standard deviation of all theoretical sample means. It's given by. Now, it doesn't quite translate as nicely as the center up there. It's not just the standard deviation. But we mentioned in class before spring break how sample size plays a role in how spread out those sample means are. So here we've got the properties that are required to describe a sampling distribution. And we're going to use those to find probabilities associated with sample means. Because if we have a normal distribution, then we can use a z-score to find probabilities associated with a sample mean. So let's do right over here. Let's do z-score for x with a bar. So you might recall the format of the z-score formula. Z equals, now I'm going to do this incomplete at first. Our very first z-score formula that we saw looked like this, where we've got the difference between an observation x and the mean. And this is in relation to its spread. So this general format still holds, but I'm just going to change it ever so slightly to not apply to a particular observation, but I just put a bar on that x so that it applies to a sample mean. Now here I'm going to actually just leave that the same because for the population mean, because over here on the center, right, mean of the sample means is just mu, so we don't need to crowd this up with any more notation. Now in the denominator for the spread, this is where I'm going to have a little bit more to add on here, because now we're going to use the standard deviation of the sampling distribution. So I'm not going to just use sigma down here, I'm also going to incorporate sample size division by square root of n. So we're going to use this formula quite a bit in the coming week or so to find probabilities associated with sample means. And in the next video, we're going to look at a particular example.